Good morning everyone. I am Sujit, working as an assistant professor in the department of ECE. This semester I am dealing semiconductor devices course for second year ECE students. And in this video I would like to cover the assignment portion for the mid 2. Already Dr. Sohel sir has covered transistors as a part of mid 1. Here I will be covering mid 2 assignments. In this video mainly I will focus on the rectifiers. Before going to rectifier, I would like to introduce the purpose of the rectifier. Nowadays we use lot of electronic devices. Most of the electronic devices needs DC supply. However, the mains give AC supply, but our devices, electronic devices, need DC supply. So the coming AC supply should be converted to DC supply so that our equipments will work with that DC supply. So we need a circuit which converts AC to DC. For that purpose we use rectifiers. Rectifier is a circuit which converts AC signal to DC signal. The main component in the rectifier circuit is PN diode. The symbol for this PN diode is shown here. It is positive terminal, it is negative terminal. Otherwise, we can call it as anode, cathode. In detail, this represents P region, N region. And this diode can be connected in two ways. One is forward bias, another one reverse bias. What is meant by bias? Bias means applying an external voltage to a semiconductor device is called bias. An external voltage or battery can be connected in two ways, forward bias or in the reverse bias. Forward bias means if the positive terminal of the battery is connected to P region and the negative terminal of the battery is connected to N region of the PN diode, then we can say the PN diode is connected in the forward bias connection. Whereas in the reverse bias, the negative terminal of the battery is connected to P region and positive terminal is connected to the N region of the PN diode. Then we can say the diode is in the reverse bias condition. What happened to the diode in the forward bias condition and in the reverse bias condition? In the forward bias condition, the depletion layer width between the P region and N region decreases, hence the current flows through the diode after a certain voltage. That voltage is called as cut-in voltage, and the cut-in voltage for the silicon diode is 0.7 volts, and for germanium it is 0.3 volts. And in the reverse bias condition, the depletion layer width increases, hence the majority carriers from the P region as well as from the N region cannot cross the depletion rate, but a small amount of minority carriers crosses the depletion region and produces small amount of the current in the reverse bias condition, and that current is called as reverse saturation current. And the reverse saturation current is very small, and it is in the order of microamperes. And this PN diode plays a crucial role in constructing the rectifier. Now we will discuss different types of the rectifiers. Now the first rectifier is half-wave rectifier. First rectifier is half-wave rectifier. Second one, full wave rectifier. Now the input to the rectifier is AC signal, and the output from the rectifier is DC. Now if you take half-wave rectifier converts half of the AC input signal into DC signal. That means for the half-wave rectifier, if you give this signal as an input, output is, means for the positive half cycle of the input we are getting the output. For the negative half cycle of the input there is no output. For the full wave rectifier converts complete AC cycle into AC signal into pulsating DC. That means positive half cycle as well as negative cycle, both the half cycles are converted into DC signals. This is called pulsating DC. Pulsating DC. It is not a pure DC. To obtain pure DC, the filter circuits are used at the end of the rectifier. Means the rectifier output is applied as an input for the filter. To produce DC, pure DC. Now in detail I will explain the half-wave rectifier operation and the full wave rectifier operation. Half-wave rectifier, the first component in designing an half-wave rectifier is transformer. It is a step down transformer and one PN diode and load resistance diode D, and the input to this circuit is 230 volts 50 hertz AC signal. Now here the input has two half cycles, positive half cycle, negative half cycle. For the positive half cycle, this point becomes positive and this becomes negative. The same polarities are established at the secondary winding of the step down transformer. Step down transformer means the secondary winding has less number of turns compared to the primary winding. Now from this, here positive is applied to the P region and N region is indirectly connected to negative, hence the diode is in the forward bias condition. As I told, if the diode is in the forward bias condition, the depletion layer width decreases and current flows from P region to N region, means majority charge carriers crosses the junction. Hence, the current flows through the diode and the current flows through the load resistor. Hence, voltage is developed across the load resistor. During the negative half cycle, this will get negative and it will get positive. The same polarities coming here. Now the diode D becomes reverse bias, hence no current flows through the diode. Hence no output will be developed across the load resistor. Therefore, in the half-wave rectifier for the negative half cycle, no output. Means only for the positive half cycle we will get the output. For the negative half cycle there is no output because diode is in the reverse bias condition. This is the working of the half-wave rectifier. Now we can calculate various parameters for this rectifier output. First parameter is DC output current. DC output current, which is represented with I DC. Next, DC output voltage VDC. As we know, the output of the rectifier is DC. At the output, DC output current and the DC output voltage are calculated. From this, DC output power PDC. Similarly, RMS current I RMS AC input power PAC. Now I am not going through the derivations of each parameter, but I am giving important parameters. Efficiency eta is equals to, it is the ratio between DC output power by AC input power, means PDC by PAC, which is equals to 40.6%. Only 40.6% of the AC input is converted into DC with the help of half-wave rectifier. Means the efficiency of the half-wave rectifier is very less. Next one, a ripple factor. Is equals to, already I told, the input to the rectifier is AC, output is DC, but the output of the rectifier consists of DC components as well as AC components. Those AC components are unwanted components and those unwanted AC components or undesirable AC components are called as ripples. This ripple factor is a parameter used to know how much AC is present in the output. Now the ripple factor is 1.21 for the half wave rectifier. In terms of percentage, 121%. More amount of AC is present in the DC. This is also one more drawback. Now, transformer utilization factor, TUF. Transformer utilization factor is 0.287. Only 287 watts of the input AC power is delivered to the load. This is also one more drawback. Basically, this transformer utilization factor is used to know the rating of the transformer. Means the usage of the transformer is also very less. Because of these drawbacks, we are going to use full wave rectifier. I am already again repeating, efficiency is very less, ripple factor is very high, the transformer utilization factor is also very low. In order to avoid these, means to solve these drawbacks, we are using next rectifier, full wave rectifier. As already I told, the full wave rectifier converts complete AC into DC. In the half wave rectifier, what happened? Only positive half cycle is converted into DC. For the negative half cycle, no output. In full wave rectifier, both the half cycles are converted into DC, so that these parameters will be improved. We will see. Full wave rectifier. Full wave rectifier uses primary winding of the transformer, secondary winding of the transformer, but it needs two diodes. In case of half wave rectifier, we need only one diode. Full wave rectifier uses two diodes and one center tap connection. This center tap connection acts as a ground. Now, both the diode ends are tied together and a load resistor is connected to obtain the output. Now, we will see the working. Input is 230 volts, 50 hertz AC signal. This is the AC signal. Now, for the positive half cycle, the primary winding gets the polarities like this, positive and negative. Now, because of this center tap connection, the voltage induced in the secondary winding is divided into two halves. First half is applied to the upper winding and next lower winding get half of the voltage induced here. Now, polarities are like this. Suppose if I am applying a voltage of V1 here, let V2 is the voltage induced across the secondary, then V2 by 2 voltage is applied to the upper winding and V2 by 2 is the voltage applied at the lower winding. Okay. Now, due to these polarities, what happened? Diode D1 and D2. Plus is connected to P region, diode is forward biased, and negative is connected to N also, N region. Hence, diode D1 is forward biased, but the diode D2 is reverse biased because negative is connected to the P type or P region of the P&L. Hence, the output is produced across the load resistor RL due to the diode D1. Is it clear? Now, for the negative half cycle, what happened? The polarities reverse, negative and positive. Now, negative, positive. Negative, positive. Due to this, what happened? Diode D1 will be off because it will be in the reverse bias condition and D2 will be in the forward bias condition. Hence, the diode D2 conducts, D1 doesn't conduct. Hence, current flows through the load resistor due to the diode D2 only. Now, in the full wave rectifier, what happened? The current flows in the load resistor for positive half cycle of the input as well as negative half cycle of the input. Whereas in the half wave rectifier, what happened? Current flows in the load resistor during positive half cycle of the input. Hence, if you see the outputs, positive half cycle, negative half cycle, positive half cycle. This is AC, this DC, pulsating DC. Same parameters we will calculate for this full wave rectifier also. Here, the efficiency eta is equals to 81.2%, whereas in the half wave rectifier it is 40.6%, full wave rectifier 81.2%. Ripple factor also improved, it is around 0.483, and transformer utilization factor TUF, it is also improved 0.61 around. Now all the parameters are improved, hence full wave rectifier is preferred over half wave rectifier. It is clear. But the problem in the full wave rectifier is use of center tapped transformer. Because of this center tapped transformer, the size becomes bulky and cost also increases. To avoid these two drawbacks, we are going to use bridge rectifier. The parameters of the bridge rectifier and full wave rectifier both are same, but the change is here full wave rectifier uses 2 diodes, bridge rectifier uses 4 diodes. Cost of a diode is very less, as we know, 5 rupees maximum, 5 to 10 rupees. It needs 2 more extra diodes, but the cost of this center tapped transformer is very high compared to the normal transformer. That's why bridge rectifier is preferred. In the bridge rectifier, 4 diodes are used. Those 4 diodes are arranged in the form of bridge. Parameters are same. Now, the assignment questions will be from these rectifiers: half wave rectifier, full wave rectifier and bridge rectifier. But exam point of view, half wave and full wave rectifiers are very, very important, and the assignment questions will be from these two topics only. Thank you so much for giving this time.